Hey everyone, and welcome back to another explainer. I'm absolutely thrilled you're here today because we are going to unpack something that is literally happening right under our noses every single second we use our devices. We're going to pull back the curtain and look at the hidden mastermind running the whole show, the operating system. You can really think of the OS as the ultimate invisible juggler. It manages this seemingly impossible number of tasks, making sure everything runs smoothly without us even noticing, performing millions of calculations in the time it takes you to blink. So let's dive into this with a scenario I think we all know pretty well. You're walking down the street, your phone is blasting your favorite playlist, it's quietly downloading a massive app update in the background, and suddenly, boom, you get a text message. All of this feels like it's happening at the exact same time. But how? I mean, we make infinite demands on our devices, right? Yet they only have a very finite amount of physical resources to work with. How does your device manage to keep up without dropping the ball? Well, that is exactly the magic we're exploring today. Here is our roadmap for this explainer. First, the multitasking illusion. Next, the CPU scheduler. Then, allocating limited resources. Fourth, contention and deadlock. And finally, the ultimate balancing act. All right, jumping right into section 1, the multitasking illusion. Okay, so when we talk about multitasking, we generally mean managing several active tasks during the same overall window of time. But how this actually plays out totally depends on your hardware. On an older single-core processor, what we have is called concurrency. Only one instruction stream can actually execute at any given millisecond, so the OS has to switch incredibly rapidly between tasks to make it feel simultaneous to us. Now, on a modern multi-core processor, we have parallelism. Separate cores can literally execute different tasks at the exact same time. But here's the real kicker. Even with multiple cores doing the heavy lifting, the OS is still the boss. It's the one managing the assignment and coordination of all those tasks to keep your whole system responsive and fair. Let's look at the big picture here. You've essentially got two massive jobs happening at once. On one side, you have multitasking, which is driven by the CPU scheduler. It's grabbing process 1, process 2, process 3, and funneling them into the CPU, switching between them to give you that illusion of simultaneous execution. On the other side, you've got resource allocation. Here the OS is acting as the ultimate gatekeeper, making sure those exact same processes get efficient and fair access to memory, your storage, input and output devices, and the network. It is constantly juggling both of these huge responsibilities. Moving right along to section 2, the CPU scheduler. Now, to really understand scheduling, you have to wrap your head around this absolutely vital key term, the context switch. A context switch is the process of saving the state of the currently running process. We're talking things like its registers and its program counter before loading up a completely different process. This is fundamentally how the OS shares CPU time. But it's a super delicate balance. If the OS does too many context switches, well, it wastes valuable CPU time just saving and loading states instead of actually getting work done. But on the flip side, if it does too few context switches, your system feels incredibly laggy and unresponsive. Let's see how this actually builds into a timeline on a single CPU core. Imagine you're running 4 apps. The CPU doesn't run them all together. Instead, the scheduler chops time up into these tiny little slices. Time slice 1 goes to your web browser. Then a context switch happens. Time slice 2 goes to your chat app. Another switch. Time slice 3 is for your music, and time slice 4 tackles that background update. This whole cycle happens so unbelievably fast that to you, the music never skips and the browser scrolls perfectly smoothly. The jobs aren't actually using the same core at once, they're just taking extremely fast turns. Which brings us to section 3, allocating limited resources. The OS is constantly putting out fires when it comes to handing out physical components. For the CPU, the typical problem is a single greedy process hogging all the time. For memory, your RAM, the OS has to decide exactly how much space each task gets, fighting against low memory or this thing called thrashing, where the system just gets totally bogged down moving data around instead of processing it. For files, the OS has to play traffic cop, deciding who is allowed to read or write to prevent conflicting access that could corrupt your data. And for devices like printers or hard disks, the OS has to manage the order of requests so you don't end up with crazy long queue delays. Now for the drama. Section 4. Contention and deadlock. The first major issue here is resource contention. This happens when multiple processes need the exact same limited resource at the exact same time. Consider this real-world example from our source material. You've got a backup process running, and it's continuously reading your hard disk. But at that exact same moment, you're trying to use a video editor to load up massive media clips.
Both processes absolutely need the disk. To respond to this, the OS has to queue requests, lock resources, or tweak scheduling priorities so that both tasks can somehow make progress, even if it means a slightly longer wait or a bit of lag for you.
But contention is just a slow wait. Sometimes things go totally catastrophically wrong. Let's talk about deadlock. Deadlock means processes are stuck waiting forever because each one is holding a resource that is needed by another one. The absolutely crucial takeaway here is that deadlock isn't just your system being a bit slow. It is a permanent circular wait. If the OS doesn't step in and do something, these tasks will just freeze indefinitely and completely waste your system resources. Think of it like an inescapable trap. Process 1 is holding on to resource 1, but it desperately needs resource 2 to finish its job. Meanwhile, process 2 is holding resource 2, but it really needs resource 1 to finish its job. Neither process can move forward until the other lets go, which they absolutely will not do until they finish. It's a permanent circular wait. It's this impossible standoff that the OS must desperately try to avoid or break. So, how exactly does the OS play the hero and fix this mess? Well, it relies on 3 main strategies. First up is prevention. The OS might impose strict ordering rules on how resources are requested in the first place, so a circle can literally never form. Second is detection. The OS actively monitors the system, hunting for these waiting cycles. And third is recovery. If a deadlock actually happens and gets detected, the OS has to break it. And that usually involves stepping in and forcefully terminating one of the stubborn processes just to free up those resources. Finally, Section 5, the ultimate balancing act. At the end of the day, a well-balanced system relies on 3 core goals. Fairness, ensuring no process gets completely starved or ignored forever. Efficiency, making sure your wildly expensive hardware resources don't just sit idle when there's actual work to be done. And integrity, guaranteeing that sharing memory and files doesn't corrupt your data or crash the entire system. And what's really fascinating here is that different systems prioritize these goals differently. A massive web server might prioritize pure throughput, while the smartphone in your pocket heavily optimizes for battery life, constantly and dynamically shifting its balancing act. I want to challenge you to apply this to the laptop or phone you are using right now. Imagine you're on a video call, you've got a web browser open with a dozen tabs, an antivirus scan is running in the background, and you're downloading a huge file. Think about the massive orchestration happening right at this second. The CPU scheduler is constantly context switching to keep your video feed looking smooth. The OS is carefully allocating memory so the antivirus doesn't accidentally crash your browser. It's managing device queues for your network card and actively dodging deadlocks between your download and your virus scan. It's all happening instantly, right behind the scenes. So, I'm going to leave you with this provocative thought from our source material to ponder. We just looked at standard, everyday devices. But why might a real-time system, say the computer flying a commercial airplane, or the one managing a medical life support machine, choose entirely different scheduling priorities from your standard desktop OS? When the stakes are literally life and death, how does the invisible juggler change its rules? Think about that for a bit. Thank you so much for joining me on this explainer. Keep learning, and I will catch you next time.